Okay, I'm gonna try this again. I tried this the other day and apparently didn't have my microphone on. So let's talk about energy flow for a little bit. All right, energy can do work against inertia, it can do it against gravity, like you can see here as far as against inertia. Here's this car right here, and basically that car just wants to stay still. So when you push against that car, you are working against inertia. Same with this box right here. It wants to stay on the ground because gravity's pulling it. So when you pick that box up, it's got weight. It's heavy. So you're working against gravity. That's why it has weight, because weight has to do with gravity. You could also work against friction. Like this person who is pushing this box, if you slide it on anything, any kind of surface, most surfaces are not going to be like frictionless, so it's going to be a little bit difficult. And then you can even work against a shape. This is showing like a shape of a spring. All right, so those are different ways that we can work against something, and that requires us to do work. So that requires energy. All right, so there are different energy forms, and you need to not necessarily memorize these, but you need to, like every specific thing about them, but you need to know these terms. So these are the various types of energy forms. You've got mechanical energy. This is like what we've been talking about with kinetic energy and potential energy. We'll talk a little bit about that some more here in a minute. We've also got electrical energy. We don't get into electricity in this class, but when you start talking about charges and currents and things that are happening inside those wires, that is a lot of energy inside of there. Chemical energy, that's going to involve like chemical reactions. If you take a beaker and you mix some baking soda and some vinegar together, it's going to bubble up, and also it might even start to get a little bit warm. That's chemical energy. Radiant energy, that is where we start talking about the sun, and that can affect so many different things. It first gives us visible light, which is what we can see, but it also is in things like radio waves, gamma waves, x-rays, things like that. So things that we can't even see. And some of those things can get really, really dangerous the more that we have. And so if you've ever heard of like radiation, that's what's coming from this word right here. That's radiant energy. And then nuclear energy. So that's energy that's involving atoms and their nucleus and nuclear reactions that's happening inside that nucleus. All right, so this is kind of what I want to get to in this video. Energy conversion, this is one more sort of math thing that we need to talk about. So energy conversion, this is where we're going from like kinetic to potential, or from potential to kinetic. So for instance, it's showing you a pendulum here in the form of a bowling ball. So this guy, he's holding this bowling ball out straight right here. And for a moment, that is not moving. So it has 100% potential energy because it's not moving. In order for it to have kinetic energy, it has to move. So as soon as it starts to work its way down to this position where it's on the ground, it's gaining kinetic energy. And at the same time, it's losing potential energy. When it's on the ground right here, it has 0% potential energy. So right here, it's 100% potential. Right here, it's 0% potential. And all in between right here, it's losing potential and it's gaining kinetic. So up here, it's 0% kinetic. And then right here, it's 100% kinetic. All right. So this can always be converted from one form to another, and it's really important to to know the concept of energy conversion. And what I mean by that is that there is just so much energy in the universe. There's just a certain amount. And it's not created, it's not destroyed, it's just converted into another form. So like in this particular case, the bowling ball is converted from potential energy to kinetic energy. Guess what? Eventually that bowling ball is going to stop. So it's not going to have any kinetic energy anymore. It was probably converted through this ground right here. There was some friction involved. Well, that probably caused some thermal energy, because if you rub your hands together, it starts to get warm. Well, that's thermal. So all of this is just being converted into another form. If I go to this next slide, that's exactly what I just said. Energy is never created or destroyed. It's just converted from one form to another. It remains constant always. And I gave you the example of the bowling ball here. Let me show you this equation that it's going to give you. So for potential energy that's lost, that's going to equal kinetic energy that's gained. Well, potential energy is still just mass times gravity times height, where kinetic energy is just 1/2 times mass times velocity squared. So if we rearrange that equation, we can actually solve for what the velocity is at any point. So if you go back to this bowling ball situation, at this point right here, we could solve for what the velocity was. At this point right here, we could solve for what the velocity was. In order to do that, we just have to rearrange this equation. So I'm going to show you that here in a minute. Actually, I'll show you that right now. Okay, so let me just do this really quick so I can write on this. All right, so it says potential energy that's lost is equal to kinetic energy that's gained. So potential energy is just mass times gravity times height. Kinetic energy is 1/2 mass times velocity squared. If I want to solve for the velocity, I just rearrange this equation. So how do I do this? Well, I'm solving for that. I have 1/2 over here. I need to get it over to the other side. So I can either divide by 1/2, or what I normally do is just multiply by 2. When I multiply by 2, that's going to cancel that. But what I do to one side, I have to do to the other. Okay, so right now I have 2 times mass times gravity times height equals mass times velocity squared. All right, so now I need to get mass out of this right side. So I'm going to divide by mass. Well, that's going to end up canceling mass. So now I have 2 times gravity times height is equal to velocity squared. Well, how do I get rid of a square? I square root it. Okay, so now I have the square root of 2 times gravity times height is equal to velocity. All right, so if I go back to this slide right here, that's exactly what we just saw for this equation. Oh, come on. Now it's going to be mad at me, apparently. It's not going to let me. Here we go. Now it'll let me write. Okay, so now we have velocity is equal to the square root of 2 times gravity times height. And so that's what this example is. At 10 meters, the velocity was just 0 because it has no motion. So if the velocity is 0, then there's no kinetic energy. Once the ball is actually released, this is like in free fall right here. So at 5 meters, we should be able to calculate what its velocity is by using this equation up here, the square root of 2 times gravity times height. And so when it's calculated, it shows that the velocity is 9.9 meters per second. One thing that I also want to mention is that the potential energy here is 98 joules, and the kinetic energy here is 0 joules. If I add those up together, I get 98 joules. At 5 meters, I can take mass times gravity times height, and I get 49 joules. And then if I take this velocity, 9.9 meters per second, then I can also calculate that it has a kinetic energy of 49 joules. If I add those up together, that equals 98 joules. Right before it's on the ground, it has basically a 0 meter height. So it has 0 potential energy, And at that very last velocity right there, it's going 14 meters per second. So if I use that velocity to calculate kinetic energy, I have 98 joules. So again, I have 0 plus 98 joules. It's 98 joules. Did I ever gain any energy? No. Did I ever lose any energy? No, because energy is never created or destroyed. Okay, let's see. Let me go on here. Okay. I think I'm going to stop the video here, and I'm going to pick up on another video soon.